Hello, AP Stats people. Welcome to part 3 of 4.2 notes. This is the last part of 4.2. We're going to keep going on with experimental design. So today we're going to talk about one of the special types of experimental design called blocking. So let's read the directions first and then I'll give you some hints. It says when a population consists of groups of individuals that are similar within but different between, a stratified random sample gives a better estimate than a simple random sample. The same logic applies in experiments. So when we were doing sampling, we talked about the idea that when we were doing sampling, that it makes sense to do stratified if you have a reason to segment up your population before you did sampling and then taking samples from each group. That is the exact same thing, except in the experiment world, we don't call it stratified. Experiment world, we call it blocking. Okay, so we don't want you using the wrong vocabulary. It's going to be important. AP graders can tell if you're talking about the wrong thing just by the use of those two words. So stratified only lives in sampling. Blocking only lives in experiments. You don't talk about stratified. If you're doing experiments, you're going to talk about blocking. And again, this is about assigning people to treatments and stuff like that. So let's show you the flow chart and kind of what that looks like. So let's say we started out with 10 people. Okay, and we decided that we're going to see definitely different results, or we suspect we're going to see different results by gender. So the first thing we're going to do is we're going to split out the people by gender. So that's this block part right here. Now, if I had 10 people, I probably didn't check and make sure I got 5 of each. So there's a really good chance that I don't have an equal amount, especially if you're getting larger experimental units numbers to start with. So in my case, I purposely made that happen. We have 4 males, we have 6 females. By the way, I'm going to write that. They don't have to be equal, ever. Okay, if we're doing random assignment, there is always a chance that we don't get equal amounts. So it's okay if you're doing random assignment to not have equal amounts. So then we're going to go into random assignment. So after they've been separated into their 2 different groups, again, I'm thinking like the evil experimenter, right? The evil scientist. It's almost like, okay, you're going to go down this hallway, you're going to go down this hallway. And then now we're going to assign them to what treatment they're going to get. So in this case, we wanted to check them. Half of them are going to get a pill, half of them are going to get a placebo. So I'm going to call treatment 1. So here's where I'm going to go ahead and make sure that I split them out. So when I do the random assignment part, I'm going to split them out, and I'm going to have 2 of them get the actual pill, and I'm going to have 2 of them get the placebo. And then in the other group for the 6 females, I'm going to have 3 and 3. If it was odd, I'd have 3 and 2. It's the best I can do. I can't split people. So 2 and 2 for the 4 males, 3 and 3 for the 6 females. Right? When we are done, we're going to measure and compare those 2 results from the genders, and then we're not going to combine, we're going to compare. That's a typo. We're going to compare at the end, what was there a difference between males and females? So I actually see comparison happening twice. Once within the male group to see was there a difference between the medicine or the placebo, and then at the end, so let's say in the male group, I see that the treatment is working, like the pill I'm giving them is definitely showing some result. But in the female group, it's not. So then I could come back and say, look, it looks to be working here, but not in the female group. So overall, what do I have to say? Probably nothing really good at the end. If I see that it's showing results in both groups, then at the end I could say, hey, look, it looks like the groups that are getting the treatments are definitely seeing a result, whether they're male or female. So sometimes we'll see that division actually give us different results, and that's kind of the point. If we think there is something out there that could significantly change our results in the experiment, you are supposed to block to spread them out so that people are alike. So if we think males are going to be treated differently or going to have different responses, they should be split out into their own group so that we can see if it works for males. Okay? If we think a factor may change results, we block based on it. So if we see something that we think like gender is going to make a difference, we block based on it, and we still randomly select and assign. And the important one, again, here in experiments, we care more about the assign than select to control. What are we controlling? We're controlling variability. And you're like, how am I going to remember that controls variability and versus bias or something, right? Okay, so remember back when we did the Justin Timberlake activity, right? When we did Justin Timberlake, right? We did what was the enjoyment factor for everybody versus what was the enjoyment when we split them out by rows. Why did we split them out by rows? Because we really thought people would enjoy it more if they were in the front row than if they were in the back row, right? So in the Justin Timberlake activity, we stratified by row. And then remember, we plotted the results on that dot plot on the computer, and what did we see about the spread? We wrote down the mean and the standard deviation. We saw that the mean was relatively close, but the spread was much, much bigger when they were all mixed together than when I stratified. So when we stratified by row, we had a smaller standard deviation, right? That's variability. Variability, standard deviation. Variance, standard deviation. Okay, those words all go together. All right, think back to example 3. I don't even remember what 3 is, but I'll go look and find it for you. Oh, it was the runners. Okay, gotcha, cool. It's the runners. What might have been something that we could have blocked based on? So was there something that maybe we could have used to say, hey, look, I think this is going to significantly change their sprint times, even if we do this extra exercise regimen, right? We think there's something else that's really going to give a different result. So what could that have been? Maybe we would have thought gender, the same way this example is. Maybe we would have thought their weight, right? That the heavier people the new program might have worked more or less than. Maybe it was their age. Maybe it was their work schedule. No, probably not work schedule. How about if it was the type of shoe or age of their shoe? Maybe an older shoe would confound the results, right? So then we block by that. We block by the age of their shoes, so that we can see and take that out of the picture and be able to compare newer shoes, older shoes while we're looking at the exercise program. All right, so blocking and stratified, 2 different worlds, 2 different vocabularies. Great. Second page, there's another type of experimental design that's called matched pair designs. And the idea of a matched pair is that there are 2 things traveling through the experiment together as a pair throughout the entire experiment. So it says a type of blocking for comparing 2 different treatments, right? That we've been doing that all along. We create blocks by matching pairs of similar experimental units. We're still using chance to decide which unit gets which pair of which treatment. Sometimes a pair in a matched pair design consists of a single unit that receives both treatments. Sometimes it's not. Since the order of the treatments can influence the response, chance is used to determine which treatment is applied first. So let's give you some examples of some things that you might want to do as a matched pair design. Let's say you were doing a weight loss program and you wanted to keep track for each person, right? Because maybe a really, really heavy person will lose a lot of weight and somebody that's really skinny is not going to lose that much weight. And you want to be able to say, like, they lost on average this much or this percent of their original body weight, right? To do that, I have to keep track of those 2 things together for each person. So maybe my first one will be my beginning weight, and then my last one is my ending weight. So I'll want to keep track of that person together, not just all the beginning weights averaged together, all the ending weights averaged together, and then say on average people lost, 2.5 pounds, right? It might be the really heavy people that are contributing to that average. So by putting them together as a group, now I can keep track for that one person how much weight they lost as a percentage of their original weight. Okay, another way to do that is sometimes we're just trying to group people because we see something similar. So maybe in that same exact example, if I only need to keep track of one data point, maybe I will pair out the 2 biggest or the 2 heaviest people as a matched pair. And then the next matched pair will be the next heaviest 2, and then so on and so on and so on. And as long as I have some kind of randomization going there, I should be okay. So I could do the randomization for which one gets the pill and which one gets the placebo, and I'm still good. So sometimes it could be like in ranking order, right? So 1 and 2 go together, right? All the way down to 19 and 20 go together, okay? And then we're still doing randomization in between of who gets which one between the pair. Okay, so here's an example. It says use the principles of good experimental design to explain how you could carry out a matched pair experiment to see if dark chocolate helps to improve blood flow better than regular chocolate. There's then this thing out there that dark chocolate could help with headaches and migraines, right? And it has something to do with the blood flow to the brain. So each subject needs to have the equal number of days where they eat dark chocolate, equal number of days where they eat regular chocolate. And it says, explain any assignment using random number table, line 101. We have 25 healthy young volunteers were used over 12 days. Now they're giving us 25. That means I'm probably not grouping two people together if I've got 25. Okay, so I'm probably looking at the same person and keeping track of something for the same person side by side. So again, in good experimental design, you would still list everything else that we did in day one. You would still list experimental units, response variables, explanatory variables, treatments, factors, levels, all that stuff first. So I'm not repeating that this time because we don't have enough room on the paper. I'm just doing the next step, which is those 4 characters of really good design. So the first one of those is comparison. What am I going to compare? Right? So my idea here is I'm going to compare the same person when they eat 6 days worth of dark chocolate versus 6 days worth of white chocolate. And maybe I'll measure their blood flow in between those when we switch. So a beginning blood flow and then a middle blood flow and then an ending blood flow. Or I could just do how much it changed from beginning to dark or from dark to light chocolate, something like that. So my comparison idea here is I'm going to be comparing results. Compare results from dark chocolate versus light chocolate based on blood flow. Okay, and again, there's a lot of different ways. This is just what I'm thinking of in the very beginning. So what's my random assignment going to be? So random assignment. Okay, this is going to take a while because they told me I actually have to explain it. So this is back to all that stuff we explained before. I'm going to have to take up some of the space from the bottom part of the paper. Okay, so how are we going to do this? We want to make sure half of them are starting with dark chocolate and half of them are starting with light chocolate, right? And see if there was a difference. So what we could do is we could use, they said I have to use a random number table. What if I use the random number table to pick out the first half of them that are going to start with the dark chocolate, and then the rest of them are going to go with milk chocolate? Okay, so that's kind of what I'm thinking about how I'm going to do this. So we're going to assign participants numbers from participants from, I'm going to have to use 2 digits, right? From 0, 1 to 25. I'm going to use table D, it's called, for the random number table, line 101. And I'm going to take 2 digits at a time. And I'm going to keep picking 2 digits until 12 or 13. Let's go at 13 participants are selected. Okay, they will start with dark chocolate for 6 days, because they want us to do this for 12 days, right? For 6 days, and then switch to milk chocolate. Okay, the rest will do the opposite. We'll start with milk chocolate for 6 days, and then switch to dark. All right, so we have our random assignment going on there. And then our next thing is control. What are we going to do to control these people so that there's not other things that are going to interfere with us measuring just the chocolate, right? So I'm going to move that down here for now. We'll move the answer for number 6 a little bit lower. So for control, let's see. Well, there's so many things that could change this. We're really mostly talking about what they're eating, right? So I would probably say ask participants to keep all other diet, food, and And let's just throw in activities, why not? Activities, woo, hello. Activities the same over the 12 days as before the experiment. Okay, something like that. And then what was our last one? Our last one was replication. So I gotta do that in pink. Replication. So in replication, we gotta make sure we have enough people that we're doing this. Now we actually, even though we're doing 13 and 12, everybody's doing some dark chocolate, everybody's doing some milk chocolate. So I'm actually repeating this 25 times. So I'm repeating this 25 times repeated for both dark and milk chocolate. Okay, and then somewhere in here, I probably want to say something about that at the end of these, maybe I should have put in a random assignment is like, what am I going to measure at the end? Measure blood flow at beginning, after dark chocolate, and then after milk chocolate. Now, even though some people are going to start with milk chocolate, that's going to keep my variables the same, right? I'm going to have a start, I'm going to have dark chocolate, and then I'm going to have milk chocolate so that I can compare the blood flow between those and then see, oh, there was a bigger difference from the start to dark or from dark to milk, right? And I can actually see the difference was it when we switched to milk chocolate or when we switched to dark chocolate? All right, so there's our experimental design. So let's go on to example number 6. It says, is the example 5 experiment a double-blind experiment? Did both the people who are eating the chocolate and the people who are given the chocolate have no idea what they were given? Well, doubtful, right? The person who's eating the chocolate probably knows if it's dark bitter chocolate or if it's, you know, the sweeter milk chocolate. So I'm going to say it can't be double-blind. So this is 6. Can't be double blind, right? Because participants can taste dark versus light chocolate. Okay, so for sure it can't be double blind. Could it be single blind? Maybe. So it could be single blind. Like I would think the person who's giving it to you could tell if they could see the color of the chocolate. So it could be single blind if the person handing out chocolate can't see it or smell it, because I think you could smell it too. Then it could be single blind where the person giving me the chocolate doesn't know which one they're giving. And again, there's still somebody else in the background who knows everything and is keeping track of everything. And then the last thing it says, could there be any confounding variables? Confounding variables. Okay, so we think eating chocolate affects blood flow, right? That's what we're trying to say. So chocolate leads to blood flow. Is that really it? Is it really chocolate? Could there be something else that could get in the way and ruin our results? Yeah, I mean, the exercise that somebody does, even though I'm trying to control for it, right? If they exercise, that could screw it up. Stress levels maybe could do something to the blood flow, right? Instead of the chocolate and screw things up. Maybe the number of work days they have within those 12 days. Maybe not everybody works the same number of days within those 12 days, and that affects things versus off days. Right? So you just have to make up something that you think could make a difference or tell them why you think it might make a difference. If I'm working, I'm going to be more stressed, my blood flow is going to be more constricted, and I'm more likely to get a headache or something like that. Okay? All right, so that is our big deal for 4.2. The last thing I want to talk about with you is just a quick reminder about this idea of random assignment and using chance to do it. Okay, I'm going to give you an example and I'm going to tell you why it's not a good idea. Okay, so let's say that I put all the names into a hat. And just for fun, let's do 20 names. 20 names into a hat. And I'm supposed to pick 10 out to get the actual treatment and 10 out to get the placebo, right? So I'm going to say that the first one goes to treatment. The next one goes to placebo. The next one goes to treatment. The next one goes to placebo. The next one goes to treatment, right? And so on all the way down to 20. Is this truly random? And the problem with this one is that my probability changes every time I take a piece of paper out of that hat. The probability changes. So it's not truly random where everybody has an equal chance to be picked. Matter of fact, when you're down to the last two, that last person that's left behind didn't get a chance at all. So imagine that I did the same thing and I said that the first 10 I pick goes to treatment, goes to the medicine, and then the remaining 10 are the placebo. Okay, now the first 10, even if I just go in there with my hand and pick out 10, that's kind of what we're saying when we say pick out the first 10, is I'm going to go in there and like count 10 on my fingers and pull them out. Okay, they all had the same random chance. They had a chance of 1 in 20 of being selected. But once we take out those 10, the rest have no chance. There is no random anything at all. So you want to be careful with this. One of the things, we're still using the idea of a hat, but you want to look at some of the things that I did before. Did I do it in this one? I did not do it in this one. I did it in the one before this one. In part 2, when we were talking about how to select things and go through the whole process of writing up something, right? That if we're using a random number table, that's going to keep everything random. Everybody always has the same chance when I'm using a random number table. If you're using a hat, again, it's that idea of everybody has an equal chance, but I would say be very careful with the hat idea that everybody is getting the same chance. Okay, that you're not taking out 1 at a time or 3 at a time or anything else. Everybody should have the same chance. Okay. So even if you would say, I dumped over the hat and just split them apart, and just split them apart into 10 and 10. Okay, now everybody still has the same chance. So be careful if you're trying to talk about taking things out in groups and leaving stuff behind. We've used, let me see if I can find the one in part 2, where we use the idea of, here we go, random assignment, put all sprinter names in a hat, mix and select 34 papers for new, 34 papers for old. Okay, so we didn't intentionally say I picked 34 out and then went back. I kind of just said I split them out. Okay, so you want to be careful that you're not giving it in some kind of order so that we're seeing the probability change along the way. We'll practice that some more in some class exercises as well, and I'll talk about it one more time. All right, that's it. Bye.